Welcome to the Deep Dive. We grab the latest research, cut through all the noise, and really try to get straight to what you need to know. And today, we're plunging into something that, well, it's super important, but it often kind of hides in plain sight when we talk climate change. I mean, the carbon stored right here in the land beneath our feet.
Mhm.
Okay, so let's unpack this a little. We are, constantly and rightly focused on fossil fuel emissions. That's the carbon we're actively adding. But what about the carbon we've actually lost? From the Earth's own storage systems, forests, grasslands, soils, they've been doing their job for ages, storing huge amounts of carbon. And a brand new study has just peeled back the layers on this. It reveals what they're calling a truly colossal hidden carbon debt that humanity's built up.
That's a really crucial distinction, you're right. And it's a critical finding.
Yeah.
This new research gives us this unprecedentedly detailed, really consistent global estimate of exactly how much terrestrial carbon stored in vegetation and soils has been, well, significantly depleted by human activity over time. It really shifts our perspective. It's not just about what we're emitting anymore. It's also about what we've eroded from the planet's own carbon reserves.
And that core insight, it's pretty staggering, isn't it? It forces us to rethink our whole baseline. The study estimates humans have depleted these global terrestrial carbon stocks by a full quarter, 24%. A quarter. I mean, that's not just a number. It feels like a fundamental change to the planet. So how does putting a number on this hidden carbon debt, this obligation we've clearly been racking up for centuries, how does that change how we understand the climate crisis,
Yeah.
especially for those of us usually looking at emissions?
You've absolutely nailed the paradigm shift this research demands.
Yeah.
Our mission here in this deep dive is really to dissect this new understanding. What does this terrestrial carbon deficit actually mean? How did these scientists figure it out with such high-resolution data? What are the main human activities driving it? And critically, what are the huge implications for climate mitigation, for our future? This new data set gives us a clarity. It lets us see this problem, which has been piling up for centuries, like never before.
So this terrestrial carbon deficit idea, it sounds incredibly important, but maybe a bit abstract for some listeners. Could you help us visualize what exactly is being measured here? How do scientists even start to quantify that gap? The gap between the carbon that is there and the carbon that could be there naturally.
It's a really powerful concept because it basically gives us a benchmark, a reference point. So the terrestrial carbon deficit is the measurable difference between the actual carbon stocks, what we find in vegetation and soil right now, and the potential carbon stocks. That's what would naturally exist, assuming, no direct human alteration, but under current environmental conditions, climate, CO2 levels, that sort of thing. So imagine a really lush old-growth forest somewhere. That's its potential. Now, if humans clear that forest for, say, farmland, the deficit is measuring all the carbon that's now missing compared to that original natural state. It's really quantifying what we've effectively taken out or stopped from building up in natural ecosystems over centuries of human impact.
And the scale of this loss, that's what really hits home, especially with the context you mentioned. The study estimates that 24% depletion of natural stocks. That's 344 billion metric tons of carbon, 344 PGC. Now here's where it gets really sobering, that figure. It's comparable to all fossil fuel emissions between 1975 and 2023. Just think about that. Nearly 50 years of global fossil fuel output just gone from our land. For those of us tracking climate news, we're so drilled on fossil fuels, this just fundamentally shifts the lens, doesn't it? It reminds us this parallel, equally massive impact we've had right under our feet. It's almost like finding a whole second hidden ledger in the climate accounting books.
It absolutely recalibrates things. Yeah. And the research breaks it down really helpfully, too, where this huge deficit mostly sits. The vast majority, somewhere between 76 and 84% of the total, comes from the vegetation carbon deficit. So that's carbon in biomass above and below ground. Think trees, shrubs, roots, everything. The rest, about 16 to 24%, is down to the soil organic carbon deficit.
Yes.
SOC. Now, while that's a smaller slice globally, SOC loss can be really significant regionally. Sometimes it's even bigger than vegetation loss in certain places, like areas with long histories of intensive farming. And what's more, this is truly global. It's not just one continent's problem.
Yeah.
Areas like China, Brazil, Europe, the US, they're all highlighted as having some of the largest deficits. It shows this is planetary.
Okay, so if we've uncovered this colossal hidden carbon debt that's been building for ages,
Yeah.
the next big question is, who or what has been driving it? What specific human activities are the main architects of this debt?
The study really lays out the primary culprits quite clearly. It reveals a stark pattern of how we use land. Topping the list: pasture expansion for grazing animals. That accounts for a hefty 30% of the total terrestrial carbon deficit.
30% just from pasture. Wow.
Yeah. And right behind that is cropland expansion, farming. That's another 24%. Then you've got forest management practices, things like logging, setting up planted forests, agroforestry. That's about 23%.
Okay.
Even urban areas, cities, and towns, despite their smaller physical footprint overall, they're responsible for a significant 3%. And the remaining 20% or so comes from a mix of other things: changes in shrublands, impacts on natural forests, not directly tied to those main categories.
And it's not just about the total area these things cover, is it? It's also about how intense the impact is per square meter, right? Like croplands and pastures cover huge areas, but their relative deficits, the carbon lost compared to what could be there, must be incredibly high. It makes you think about the landscapes you see every day, that huge ranch, that endless field of corn. They look, productive on the surface, but underneath there's this deep carbon history we've just paved over.
You've really hit on a crucial distinction there. It's not just the extent, it's the intensity of carbon loss per unit of area. And the relative deficit numbers really bring that home. For croplands, the actual vegetation carbon density is, on average, a shocking 81% lower than its potential.
81% lower.
Exactly. And for pastures, it's 73% lower. These figures show just how dramatically we transform ecosystems and basically drain their carbon storage. And while cities, urban areas, are a smaller total percentage globally per unit area, they have the highest absolute vegetation carbon deficit, 72% loss of potential. The basic reason for these losses is pretty straightforward, really. When you convert natural ecosystems like diverse forests or grasslands into, say, monoculture farms, or manage them really intensively through logging, you release stored carbon from both the plants and the soil into the atmosphere, and you often prevent that natural long-term carbon recovery. Forest management, for instance, even if it's for timber, can end up having a negative overall effect on soil carbon if it's not very carefully designed with carbon sequestration in mind.
Okay, so it's one thing to get this incredibly detailed high-res picture of our carbon debt, clearer than ever before. But the immediate question then is, how does this new reality check out against the tools we use to predict our climate future? How do our established climate models, these dynamic global vegetation models, how do they actually stack up against these new findings?
Well, this is genuinely one of the most critical and maybe worrying findings in the study. It shows a pretty substantial discrepancy. These dynamic global vegetation models, DGVMs, they're widely used in Earth system science, right? To simulate carbon cycles, project future climate. They significantly underestimate this terrestrial carbon deficit. On average, they're off by about 37%. Some models underestimated by as much as 58%. That's a huge margin of error.
37% on average. So what does that actually mean for how we understand climate change? If our main models are undercounting this massive hidden carbon loss by that much, aren't we essentially missing a huge piece of the puzzle? It sounds like we might be underestimating the sheer scale of the challenge and maybe even thinking we have more time than we do.
You've precisely grasped the implications there. Yeah. This underestimation strongly suggests that the DGVMs are likely underestimating carbon fluxes. That's the movement of carbon in and out of the atmosphere, specifically from land use and land cover changes, or LULCCs. So they're probably undercalculating the carbon released when, say, a forest gets turned into a farm or a city.
Right.
And if that's true, it implies that the remaining carbon budget we think we have, to limit warming to that critical 2°C goal, it might get used up earlier than we thought. And looking at it the other way, it also means these models might be underestimating the potential benefit of carbon removal through restoring vegetation and soil.
I see.
The reasons for these discrepancies in the models are complex. It's down to differences in their internal structures, how they simulate different ecological processes, their parameterization, which you can sort of think of as the specific settings or dials that control how the model behaves, and even potential errors in the actual LULCC forcing data itself, the historical land use data fed into the models. For example, a lot of models don't fully capture all the relevant processes, like the full extent of human-caused fires or some of the more subtle ongoing forest management impacts.
Well, what's fascinating here, though, is that this new research isn't just pointing out a problem. It seems like it's offering a way forward, too. This high-resolution data could actually help improve those very models, right? Give them new constraints, reduce the uncertainties, and give us a much sharper picture.
Exactly. That's a key point. This new high-res observation-based dataset isn't just descriptive, it's a powerful tool. It can be directly used to help refine and constrain the DGVMs, improve their ability to simulate the deficit accurately, and consequently, improve their projections for future climate and how effective different land-based mitigation strategies might be. It's like a feedback loop for better science.
So given this profound degradation that the deep dive has revealed, I mean, centuries of activity leading to this massive carbon deficit, what does the research tell us about how we move forward now? What solutions are out there? What urgent actions are needed practically and from a policy angle?
Well, the study unequivocally underscores the urgent need to prioritize conservation and restoration efforts on a massive scale. And it stresses the need to guide sustainable land use decisions globally. For instance, the coming Montreal Global Biodiversity Framework, its target of protecting 30% of land and sea by 2030, that's highlighted as absolutely crucial. It's not just about biodiversity, it's also critical for safeguarding and restoring these vital natural carbon stores.
Okay, so protection is key.
Right.
What about specific strategies?
Yeah, the research also points to specific science-backed strategies that offer real pathways forward. Things like land use efficiency. Basically, getting more agricultural output from the land we already use, reducing the pressure to convert more natural ecosystems.
Makes sense.
Minimizing food waste is another huge one. It directly cuts the overall demand for land-intensive food production. Dietary changes, too, particularly reducing demand for things like meat, which use a lot of land, that can make a big difference in freeing up land for potential restoration. Then there's improved forest management. Not just managing for timber, but specifically focusing on locking up carbon. That can help offset some remaining emissions. And finally, even though it's a smaller global driver, the rapid spread of urbanization needs more focused attention as a really significant local driver of carbon deficit. Each of these holds potential, from farming efficiency to diet shifts, but they also bring complex challenges in how we actually implement them. It needs global cooperation, local adaptation. It's not just about knowing what we can do, but figuring out how we mobilize globally to make it happen at the scale that's needed.
This brings up a really important, almost daunting point, though. Ecosystems, they can take decades, sometimes centuries, to fully recover their natural carbon potential.
hmm
How does that recovery timeline clash with our immediate, really ambitious climate targets, like getting to net zero by mid-century? It feels like we're racing against time, but nature's clock just runs slower than ours sometimes.
That is a profound challenge, you're right, and it really highlights the long shadow cast by our historical impact. The study emphasizes that the sheer scale of human intervention needed to restore all that lost carbon is just
Goodness.
massive, absolutely massive. This estimated deficit is so vast that even when you compare it to projected future carbon removal tech like BECES, that's bioenergy with carbon capture and storage, growing plants, burning them for energy, burying the CO2, or even the huge afforestation and reforestation efforts people talk about needing by 2100 to meet the 2-degree C targets, this historical deficit is still a huge chunk of that picture. Our long-term impact demands a long-term sustained recovery effort. And yes, that natural recovery timeline is definitely at odds with our urgent climate goals. It means we have to not only stop the bleeding, stop further loss, but actively engage in restoration at an unprecedented scale and recognize it's going to be a multi-generational task.
Wow. Okay, so the core takeaway from this deep dive seems crystal clear. The human impact on global carbon isn't just about smokestacks and tailpipes. It goes way beyond burning fossil fuels. Our choices about land use, stretching back centuries, have created this almost equally significant carbon debt, a hidden, massive historical disruption to our planet's natural systems that we're only now really getting a full measure of.
That's precisely it. This study is incredibly important because it gives us that consistent, high-resolution picture of this hidden debt. It provides a much clearer understanding of the deep, long-standing impact human land use has had, and its critical implications for how we accurately model climate change and how we design our mitigation and restoration strategies going forward. It really is a foundational piece of the climate puzzle.
So what does this all mean for you, listening right now? When you look at the landscapes around you, maybe a farm field, a managed forest, even your local city park, try to consider that hidden history of carbon beneath your feet. And think about the potential that might still be locked away or could be restored. This research reminds us that our collective decisions about land, they aren't just about what we grow or what we build. They're about the very balance of our planet's carbon cycle.
Yeah, this deep dive into our terrestrial carbon deficit really shows us the profound long-term impact of what we do on Earth's natural systems. It's a powerful call, really, to fundamentally rethink our relationship with the land and to truly grasp the immense scale of the conservation and restoration efforts that are actually needed to start mending our planet's hidden carbon wounds.
So a final thought to leave you with. What actions, big or small, do you think could start to chip away at this immense carbon debt?